Okay, now I want to take I want to pause a bit, and I want to jump into something about computers. This whole field, and lots of others, has evolved over 50 years because of evolution in computer technology. If you think about that evolution, there are two steps in it. One is completely obvious. In the early days of computers, up until about the 1980s, this was the model. You had a bunch of people, and they interacted with some giant box. Okay? They went there, they dumped something there. Most of you are much too young to know what a punch card is, but they went there. The computer was this central palace, okay? And the people were there, and they were connected wires. Okay, what happened in the 1980s is that computers became cheap and small, and you now got this model. You have the same people, many more of them, but they're all holding it or next to it or something, whatever. In a sense, these two models are exactly the same because there is a one-to-one association of user and computer. That's what's changing in the second revolution. Second revolution, this slide, is exactly the same, except that you're now holding several computers. And in a few years, you'll probably be several dozen. But you're holding a computer, but now you're interacting with something that's actually doing the work. And that association of user with computer is now weakened because you actually don't know who's doing the work. And if you carry that to the extreme, you could see some very interesting things coming up, but I don't want to carry it too far. So let's talk about a mobile device. Mobile devices have two ways that they're used, and all you have to do is go on a college campus and watch people who are 20 years old using cell phones, and you'll see exactly how they're being used. They're being used for instant gratification. I'm going on the web, I'm buying something, I'm surfing instantly. Intel has actually defined the word instant as 300 milliseconds. If you have to wait longer than that, it's too long. Okay? So that's one way. The other way is instant notification. And that is that I submit something from my mobile device. I expect to be notified that I've done that or acknowledged, and then as soon as your such and such has been sent, and as soon as there is a response available, I expect to be notified of that response. Email, texting are examples of that. Texting is actually in the middle. Now, that's how they're used. Now, unlike conventional PCs and Macs and cell phones are really different. The devices I'm talking about are not meant to actually stay connected or to go back and forth, actually do the calculation or to hold the phone conversation. They're really intended as input-output devices. That's a personal bias. All right, now let's look at quantum mechanics, modeling. Instant gratification is not going to happen. You can't do quantum mechanics in a second. Not with a cell phone or an iPad, not with any computer that presently exists. We're talking about minutes, hours, maybe longer. Okay, those are non-tolerable numbers. So we're not going to be able to do that. What we can do is we can use databases, and what we can do is we can make a question, and if that question is in a database, we can return that. Let me just give you a very simple example of that. I'll go back to here so we can build something. I'm going to make another point, how easy it is to do modeling. I'm going to build a simple steroid. I have a philosophy, if it takes more than about 1 minute to build anything, to construct an input, it's too long. So I built, if I haven't made any mistakes, I built a simple steroid. I'm going to now bring it into a 3D world, and I'm going to access it. Okay, if it's in a database, it's there. Once I have it, I have its properties. So I have its infrared spectrum. Okay, if I were connected and there was an experimental spectrum, I can't do that on the iPad. I could pull that in. If I want a carbon spectrum, I could pull that in. If I wanted some, I don't know, people love molecular orbitals, I could pull those in. I'm actually pulling in the ability to calculate, I'm calculating. So basically, you can use this in a way where I'm actually accessing from a data set. Now, let's get back here. What I've shown you there, and I want to make this very clear, I'm playing with an iPad. You can't really do calculations on that. When I talk about calculations, what I'm actually going to be doing is connecting to a server. And so, not one in the sky, it's going to be one in California. Not important. So what I'm doing here is a very tiny subset of what can be done. The other mode is what I'll call instant notification. This is, I'll submit a calculation, and when it's done, it will tell me. So let's just do that. Let's go back here, and let's go back here. And for fun, I'm just going to I'll put another methyl group on here somewhere. I'll put a methyl group here. And let's assume I don't have that. And I'm going to make a request to the database, and it's going to say, I don't know about you. I don't have you. So what I'm going to do is I'm simply going to say, well, let's calculate it. I'm going to say compute, and it's going to submit this to someplace in the sky, in the world. And it's recorded that it's being submitted. It's somewhere recorded that it's being submitted. It's there, and when it comes back, it will tell me. Okay, it may happen by the end of the talk. It may not. I don't care. But the point is that you can accommodate things. All right, let me do one more topic. How much time? I'm going to touch on the topic of kinetics. Kinetics is a funny one. It's a funny one because what we can actually calculate and what we can measure are entirely different. The concept of the thing in between the reactant and the product, the transition state, we can't measure that. It doesn't exist. Even the concept of an activation energy, we can't really measure that because what you're measuring is actually not an activation energy, but that times some other quantity. So it's a little bit foggy there. What you can calculate directly is structures, what things look like in between. A transition state and an equilibrium structure are no different. They're just well-defined points. And you can actually calculate energies. Let me just give you one example. Transition state structure in one dimension is just this curve that we draw all the time. I know chalk. It's the curve where we draw, we draw a bump and what have you. It's the bump. In many dimensions, it's more complicated because it's actually not a maximum. A transition state is actually a maximum in one dimension and a minimum in all others. But in any event, we can calculate. Now, I'm not going to give you any examples of that. The example I'll give you is the contest that chemists have between kinetics and thermodynamics. And I'll give you two examples of this. We have two diagrams that chemists love to draw. One is the notion of I have a reaction going over two different places leading to two products. The thermodynamic product is the one at the bottom. Period. Completely well defined. The kinetic product is the one that goes over the smaller hill, whether it's at the bottom or not. This is very ill-defined because it's the fastest generated product. But what do I mean by fast? Where do I stop? If I stop long time, I'll get much more of this than that. If I stop short time, I'll get mostly reactant. I'll get much more of that than that. So kinetic product is ill-defined. Even if it's ill-defined, we have lots of. The interesting thing about it is that where the kinetic and thermodynamic products are different, we can, by controlling time, temperature, we can actually push a reaction one way or the other. All chemists know that. Let me give you two examples. I'll give you a textbook one and the real one. The textbook one, I'll skip that slide, I just said it, is that if I take, this is very simple. If I take one bromohexene and I heat it up in the presence of something that can make a radical, and then in the presence of something that can contain that radical, I should get this. So I'm going to make the radical, I'm going to rip bromine off, and then I'm going to add hydrogen, essentially, by that. I'll get one hexene. That turns out to be a minor product. It's a minor product because once you have that radical, it lives long enough that it can actually close by attacking either that carbon or that carbon to give you that radical or that. Thermodynamics would immediately tell you that if this process happens, that is the problem. That radical is much better than that. Elementary organic chemistry will tell you that. However, that's almost zero product. The dominant product is here because this is the kinetic radical. So this is a very clean example. Let me give you a much prettier one that's much less clean. This is an example that comes out of Exxon about 20 years ago. If you buy cyclobutadiene, it's in the form of a dimer. At least that's what the bottle says. The question out of Exxon was, how do I make a polymer? And if you try to polymerize it, it polymerizes, but it stops at 20 units. If you think about that for a few seconds, you'll come up with the answer. Completely wrong answer. The answer you'll come up with about 20 seconds thinking, if you draw this, it's linear, and so shouldn't stop. If you actually build this in a Spartan or whatever, it's curved. And when I was asked this question, I was very lazy. I built about 3 units. It's hard to build. I built about 3 units of it, and I convinced myself it was curved. And, fine, end of story. However, if you build 20 units of it, you discover that it's curved, but it's a helix. And so this polymer is perfectly fine. If I had been a little bit more cognizant that I really am an organic chemist, I would have recognized the answer to the problem much earlier. I've drawn you the exopolymer. There are 2 stereoisomers. The kinetic stereoisomer is the endopolymer. If you make the endopolymer, it's that. The beautiful thing about this is that a little bit of thinking, a little bit of just building 3-dimensional structures would have told you rather quickly that The reaction to stopping is an endopolymerization, which you should know anyway. And if you want the other one, just heat it up. If you just go under hotter conditions, you'll actually get the thermodynamic product. Exxon actually did that. Oh, I'll just have to bring that up. We worried a lot about the kinetics of butadiene polymerization. Let me skip that. Okay, my last couple of slides. Modeling. Modeling's now been around for a long time, 40 years. In the last 10 or 20, it has become rather powerful because technology has become rather powerful. Why isn't it more commonly used? And there's a set of excuses. I hear lots of excuses. And the simplest one is that it requires very powerful computers, and I don't have them. Well, that statement is half correct. It does require very powerful computers, but you do have them. Your cell phone is more powerful than a Cray or Fujitsu of the 1980s. And what is commonly brought around as a laptop or something is orders of magnitude more powerful. All right, so yes, it's true, but right now the computers that one can get for very, very little are quite capable of dealing with real molecules. Second excuse is that molecular modeling is intimidating. By that I mean you begin with the word quantum mechanics and everyone gets frightened. Quantum mechanics. I took that in physical chemistry and almost failed it or something like this. You get those comments. I should remind people, and I speak in front of synthetic chemists a great deal, that NMR is based in quantum mechanics, and in fact, its base is much harder than the Schrödinger equation. It's time-dependent Schrödinger equation. You don't really need to know the quantum mechanics to use NMR as an effective tool. And I think that's the exact same thing with modeling. You do have to know the capabilities of the NMR. You do have to know the capabilities of the model. You don't really have to know the details. Third one is molecular modeling is unfamiliar. Chemistry is a 3D world. Chemists are amazingly a 2D population. They love to draw. I have no problem with that. And you can see in this little last demonstration I gave that drawing there's nothing wrong with drawing. And so we've worried a lot about interfaces that can now draw. And once you do that, I should make it three-dimensional, but why not? Once you do that, the 3D part can come pretty automatically. So it shouldn't have to be that. The point I've tried to make in the whole talk is my next to last slide. And molecular modeling not relevant. That's the most common comment. In fact, what I've tried to show you is there are a few areas, and there are 5 or 10 areas where I believe that modeling can actually be really relevant in a very purely routine way. I tried to show you assignment of NMR spectra or challenging NMR spectra, things like thermochemistry. Okay, my last slide, before I thank you all, is the notion of a learning curve. Like everything else in science, there is a learning curve. It's not very large. It's much smaller than it was a decade ago. There are frustrations. Everything one tries doesn't work, just like every experiment one tries doesn't work. But I think it's one of these things that if you begin to experience modeling, you begin to realize that it's a rather natural approach. All right, I'll quit now. My slides are actually on a website. Thank you very, very much.